Hi everyone. So the lead good question for today says that we have to count the number of complete components. So in here we are given an undirected graph and we're given this 2D array of edges. So we have to return the number of complete connected components of the graph. So there are two parts for this question. The first part says that we have to find the number of connected components. And then the second part says that those connected component have to be complete. So what's a complete connected component? It basically is like, let's say for every edge, for every vertex, that's it has to be connected with every other vertex in the connected component. So there are two parts for this question. We see first part is to find the connected component and the second part is to see if it is complete or not. So firstly, our intuition comes down to let's build a graph. Let's use an adjacency list and we'll just build a graph, right? And then we'll use traversal techniques to find the connected component. Now, the standard way to find the connected component, we can go about this in three ways. We can either use like a BFS or DFS or union find. So a very clean way to do this and very intuitive ways, like we can use BFS or DFS. So let's choose BFS for this question. Now, then we need to find the connected component. Now, there are two ways to find a complete connected component. So basically, let's say we have this connected component, right? So then if like, let's say how many edges are there? Sorry, how many vertex are there? So we have three vertices. Now, every vertex, let's say we have total number of three vertex. So every vertex must be connected to total minus one vertex except itself. Why not equal, like, what's the total number of vertices here? 3. Now, 0 is connected to how many vertices? 2. Why not 3? Because uh, it's not connected to itself. That's why every vertex must be connected to total number of vertices minus 1 vertices. The other option is, so the first option was what? We have to count the edges for every vertex. And the second option is that we can go like let's say this is a complete graph. Now we have to find the number of edges between vertices. So the formula goes down to be v into v minus 1 by 2. Implementing this is easier. So we are going to choose this and we're going to skip this. So let's see how do we go about the process. So the first step here is to build an adjacency list. So let's create a listed list of integers. Let's name this graph. Let's build a graph. So for every vertex, for every node, we are going to create a new array list, empty array list. So we're going to simply append array list at the end of the graph, correct? So this is how we do it. Now what we do, we build a graph. How do we build? So our source is edge of 0 and our destination is edge of 1. Now a graph dot get source dot add destination. Correct? Now same. since this is a bidirectional graph, undirected graph, right? So now we're going to get destination and add source. So now that we have built a graph, now let's traverse. So before traversing, let's have a global visited array of Boolean data type, which will keep a track of what vertices have been visited. Now let's use BFS. So let's use the standard queue. We are going to use linked list implementation. So now let's start from every index and see if we have visited that index. So if we haven't visited a particular index, it means we have to start our traversal. So let's offer I to the queue and start a BFS traversal. So while our queue is not empty, what do we do is we let's also have an array list which will contain the connected nodes. I'll tell you why. And why a list and why not a set? The reason is that if we use a hash set, there will be, you say hash calculation, then we have to handle the collisions and all of that. But if we use an array list, and since we're already using visited, we are not going to, enter. We don't have to have worry about if we are going to add an element twice, if about the duplicate elements, and that's the whole thing that the set does. It does provide us the it ensures that we do not have duplicate elements. But in array list, we just append it to the end. And in set, if we'll have a lot of burden on the, runtime burden would be added of, calculating the hash and then, you know, handling collisions, etc. So that's why we're using this list. Now, what we do is we have this current node. Let's pull this from the queue. And let's add it to our connected nodes. Now, what we do is we check the neighbors of the connected nodes. So how do we get the neighbors? We'll get it via a graph, right? So for in neighbor, and we have this graph. So let's get current node neighbors. And we can check if the neighbor is unvisited. Then what we do is we add it to a queue. Queue dot offer neighbor. And we also mark it visited. Right? So that there are no duplicates added. And we continue this. Now, after coming out of this, we have got a connected component, right? Now, when we have got a connected component, we need to check if it is complete. So let's check if it is complete. Now, let's say I will have connected nodes, right? So let's say for every connected node, in connected node, let's check if, let's calculate the total size of the connected node. So size is equal to connected node dot size. So now since we've calculated the size of the connected node, what do we do is we check that for every node, if let's say my graph dot get node dot size is not equal to size minus 1. It means that there is some element which is remaining. It's not connected to all the other nodes. There is some vertex missing. Sorry, so there's some edge missing. So that is why we are going to say that let's also have a Boolean variable called is connected. Set to false, set to true. Now here we'll say this is not connected is equal to false, and we are going to break, else we'll keep on checking. Now after we come out of this loop, we are going to check if the connected components are connected, is complete. Sorry, this complete is a better word. So we'll check if all the connected components is complete. If yes, then what are we going to do is we are going to now since that is complete, it means that we have to add, we also need to keep in complete component count is equal to 0. So now we need to increment the complete component count. Okay. And in the end, when we come out of the loop, this loop, we are going to return complete component count. Now let's run this. Okay. This has to be integer. This has to be an array. So let's see where the error is. So there's one thing that we missed. We added I to a queue, but we forgot marking it as visited. So now since our code is running, let's see if it passes all the test cases. And also, let's also see our time and space complexity. So in here, our time and space complexity is, so our time complexity is big O of V plus E, where V is the number of vertices and E is the number of edges. And our space complexity is also big O of V plus E. Why? I'll tell you why. So we are iterating this for big O of E times number of edges, and this is big O of V, and this is also big O of V. This is as well big O of V as a data structure, and now we are going to have this queue until queue is empty, all of that. So every vertex will be processed once. So in here, and we're going to add every vertex once to the queue, and then we'll have to our current connected nodes, every vertex will be added once. Now when we talk about this, it will go for big O of V, correct? So that's why our time and space complexity is big O of V plus E. This is like required for our graph that we've built. And Yeah, that was it from my end. Thank you.